So my dear friends, I really welcome you to my new YouTube channel, Amir Kim Zone. And today we are going to discuss some of the most, in fact one of the most important and you can say basics of organic chemistry. It's quite distressful when I see students talking about SN1 and SN2 mechanism. They say, I want to leave this topic, I'll leave this topic. So why I cannot understand SN1, SN2 mechanism? What is there? So I want to leave this topic. So what if this topic is removed? These are the general questions that are asked by my dear students. So for them, today I'm making a video which is quite comfortable and which will definitely help you out. There are two parts, SN1. By the name suggests SN2 and SN1, although it is quite difficult to understand at this point, but let me give you an idea. Here N stands for nucleophilic substitution, second order. Again, nucleophilic substitution of second order. You'll have to write it down. You'll have to write it down somewhere so that you can recall or remember, although you have the video. So, and the second part is nucleophilic substitution of first order. Now, before we start SN1 and SN2, I would like you to take you back in the chemical kinetics. There you had a concept of order of a reaction. Remember? Yes. So let us take an example. Rate of a reaction, suppose we have A plus B gives C. If we'll have to write something according to law of mass action, rate is directly proportional to the concentration of reactants. That means if we have reactants, the rate will be dependent upon the concentration of reactant. So as to say, if we want to increase the rate of the reaction, we'll have to increase the concentration of reactant. In this case, we have reactants A and B. So if we increase concentration of A and B, the rate would definitely increase. Or we can say the rate is dependent upon the concentration of A and B. Now, did you get my point? Rate is dependent upon the concentration of A and B, or we can say rate is directly proportional to the concentration of reactants. This is what we have understood so far. Now let us take two examples. We have methyl chloride. Here we have aqueous KOH and it gives us a simple form of nucleophilic substitution reaction, no need to wonder. We get alcohol and we get KCl. The same reaction is here, but in this case we have tertiary alkyl halide which is reacting with aqueous KOH and it is producing tertiary alcohol. You'll be amazed to know there are two reactants. There are two reactions, methyl chloride and aqueous KOH. If these are the two reactants, the rate has to be dependent upon methyl chloride as well as aqueous KOH. Right? In this case, the rate has to be dependent upon tertiary chloride and aqueous KOH, both. But in this case, we have a rate which is dependent on CH3Cl plus, or we can say OH minus. We can say both the reactants are involved. But as far as tertiary chloride is concerned, our rate is only dependent upon tertiary halide. Where is the other reactant gone? That means our rate is only dependent upon the concentration of tertiary halide. It is not dependent upon aqueous KOH. So if we increase the concentration of aqueous KOH, which is our reagent, will the rate increase? No, you have the capability. We said rate is dependent upon the reactants. So if we have the idea in tertiary halide, rate is proportional to the concentration of tertiary halide only, not on aqueous KOH. That means if we increase the concentration of KOH, it will not affect the rate of the reaction. Understood my point? Now the second most important part is, if we increase the concentration of tertiary halide, the rate would definitely increase. Why two different mechanisms? Why methyl chloride is not following the way as tertiary halide is following? Or we can say, why tertiary halide is not following the case as with methyl chloride? So let's start. Guys, for more interesting videos, all you need to have to subscribe is my YouTube channel and hit the bell icon so that you get the notifications as my new videos are on the YouTube channel available for you.